share my screen. Oops. Can you all see the full version, or are you seeing my notes version?
I'm seeing the notes version.
Okay. Hi.
So if you go to display settings, and then there's swap presenter and slideshow view. There we go.
Thank you so much.
Yeah, no worries.
Okay, so hi everyone, and welcome to an introduction to network analysis in R. I am Dozal, and I am a second year, I guess going into my third year next semester, PhD at the School of Information. And yeah, I'm very much into network analysis theory, and using applications is a really cool way that I've found this past semester, a really cool method I found this past semester. So network analysis and graph theory and stuff like that. So let's just get started. Okay, so before we start, there's a link in Zoom for y'all to go to the GitHub and download the content, and hopefully you all already have our studio. But so essentially, you should be at this page from the link. Please let us know if you can't see this page, but you should be here and really just click download code, and you should get all of these documents, or all these files rather, so we can start working on that. Please let us know if you have any problems. I'll try to open my chat here. Yeah. Cool. So, and while we're all doing that, I will kind of go over what you all can expect from this workshop. So this workshop is for beginners. So if you don't know anything about network analysis, or you kind of understand and you're still looking around, this is for you. This is the introduction to network analysis. We're going to learn basic foundational concepts. We're going to learn how to apply the concepts in R, and we're going to look at how to interpret the outputs. There won't be any equations, and the textbook definitions for a lot of the concepts that we're going over will be included. Code is included, and also references. So this morning, we're going to try to aim for an idea of what network analysis is, essentially what it can be used for, and this is a great entry point to see if you're interested in this topic, and if you think it could help with your own research and work. Please send us messages in the chat, questions. You can also just kind of cut in and ask me questions as we go along. So, okay, networks are everywhere, and just like we were talking about earlier, they seem to be even more popular because of the internet and social media and just online connections. But aside from the internet, you could find networks in essentially everywhere around the world, or in your environment. So metro stations, transit, networks are really popular to look at. Shipping networks, so trade is also really, trade and economy have been really popular topics in network theory. And also ecosystems, so marine life, animal life ecosystems are also popular in how different animals interact with each other. And so essentially we're looking at how specific actors within a network interact with each other and how those relations work. So the bare minimum, we have two main players in network analysis. We have a node and we have an edge. Nodes are, so nodes are usually called vertices or actors. And so, sorry. So here are the circles. So Mark, Lisa, Emma, and David, they're nodes. They can also be called vertices, actors, or these three things. Edges are what links nodes together. So edges are also called links, ties. And so we know there's a relationship between Mark and Lisa as both as nodes or actors. And they are connected by an edge or a tie. And so a graph, a network graph, is made up of nodes and edges. So further into kind of like the relationship between nodes, edges can be undirected or directed. So we can have here, let's say we're in an advice network. So David gives advice to Emma, but Emma does not give advice to David. So the direction goes from David to Emma. And then we have here, Emma and Lisa give advice to each other. And essentially, because they're unweighted, that means that the advice is, I guess by default, we're going to say it's weighted equally. So it would be the same thing, 1-to-1. And we also have weighted or unweighted. So obviously weighted means like, well, I guess not obviously, but you can have different weights for relations. So if one relation can be less important than another, and the more weight, the more importance it has. And we can also apply a weighted and directed edge to the graph. So here, again, with our advice example, David gives Emma advice, but it doesn't seem to be as important as the advice between Lisa and Emma. And like I said before, in a lot of network analysis, you're going to hear nodes being referred to as vertices or actors, and edges will be referred to as ties or links, depending on the field. So network graphs can also be bipartite or unipartite. Unipartite means there's one set of similar of nodes. So we have, continue our example, we have people. So unipartite is a graph full of people. Bipartite can be a graph full of people and maybe clubs. So our advice givers and receivers from before, maybe some of them are part of, let's say, a karate club, a cooking club, a book club, what have you. And so that can be, so the people to clubs is an example of a bipartite network. But you have, so for a in a bipartite network, every edge must connect to another set of nodes in both sets. Every edge must connect a node from one set to another, excuse me. And what we won't cover this morning is hypergraphs and multigraphs. So hypergraph is a generalization of a graph in which an edge can join any number of vertices. So here we have an edge that's split into two nodes. So instead of going from 1 to 1, we have this edge go from 1 to 2. And a multigraph is a graph where multiple parallel edges, so different types of relationship, can connect the same nodes. And here we can allow loops. And a loop is a node that is connected to itself or has a relation to itself. These two types of graphs are mainly used for advanced graph theory, mathematics, and kind of deeper network analysis applications. I might have added an example in the notes. Like you're going to get all my notes also, so I might have added an example in the notes. If not, I will do that after this. And these types of applications have also been used in specific, some deep learning. So when we're looking at graphs, we also want to use their data formats and be familiar with how their data formats are made up, because that's essentially how we do a lot of our analysis, right? We're not just pointing and looking at a graph, we're looking at the data. And so we have two forms of data that we can look at and work with. First is our edge list. So this is up here. And we're looking at essentially who is connected to whom. So Mark and Lisa. Lisa is connected to David. Lisa is connected to Emma, and Emma's connected to David, and within this graph. And then we have, edge lists will list every tie in the network. And each row corresponds to a tie that goes from the node listed in the first column, so Mark, and the node listed in the second column. And these edge lists are usually more efficient for larger networks to like process and analyze. Here we have on the bottom an adjacency matrix. It's also known as a sociomatrix. So there are square matrices, so you need to have the same number of rows as columns, where one indicates a tie between the two nodes. So Mark and Lisa is here, and here's a 1. And 0 indicates no ties. So what there is to note here is that the diagonal is all zeros. So here, that means that the network is undirected. So I guess, sorry, to step back, to read this, you start with the rows that send information and columns that receive the information within a directed network. If a network is non-directed, then the sociomatrix would be symmetric and diagonal. So here we are. For a simple network, there are no self-loops where a tie connects back to its own node. So if Mark connected back to himself, there would be a 1. Oh, yeah, okay. So today we're going to look at a network from network data from a study done by Zachary in 1977. It looks at the social network between members of a university karate club, and the members or the club connections and relations were observed from 1970 to 1972. And the way that we look at links or relations within this network is if the two actors interact outside of the karate club. And so we have our two formats. A is our edge list. And this is not, these are just snippets of the network. It's not the full network because I believe there are 31 members that were observed. And so I think that would be a lot. Yeah. So I don't know if there are enough of you, but if anyone wants to go, I think I just said this was our edge list. So what format is B in, if anyone wants to take a try at that? Well, I know it's the morning and there aren't very many of us, but B would be our socio matrix or our adjacency matrix. And this network is going to be undirected because we have a diagonal of zeros here. Like I said before, this is kind of cut short. So it's not the full matrix, but if you were to see it in its entirety, the zeros would be a diagonal across. And here we're looking at an unweighted network. They're all ones and zeros. And for this, because it's a smaller network, 31 ties, where we would prefer B, the adjacency matrix. A couple side notes on the data. The original data set didn't contain any names, but names were added by the person who kind of imported this data into the R package. And so it was strictly for educational purposes, and they're random. Okay, so let's get to the fun part. Let's go to R. And I have it all set up here. So essentially, I'm just gonna start over. Oops. So we could all be on the same page. Okay. So,
right. Laura, do you mind making your Zoom window larger?
Yes.
Like if you go to view and zoom in, you should be able to.
Oh.
Or even just increasing the text size a little.
Oh, yeah. Definitely. Oh, Control++. Nope. How's that?
Maybe one more step if you can.
Sure.
Yeah. Yeah, that looks good to me. Thank you.
Awesome. Yeah, thank you. Okay, so my environment is empty, so please let me know. Please stop me if you have any problems going to the code. We're going to use 3 packages for this script. We're only going to download 2. Later on, we'll use another package. And I don't know if some of you all know, but sometimes when you download, excuse me, not packages, libraries. Sometimes when you download multiple libraries in R, they can conflict. And so a lot of times you'll get libraries overriding some of the fun functions of another library that you might have needed early on, and so we'll find a way to kind of get around that later on in this. But okay, so we can start downloading StatNet and GG Alley. I've never said those out loud, actually. Okay, and also if you all want to kind of, I guess you have this with you, but I'll go through it and describe it. But I guess if for some of you who want to be kind of hardcore at this, you could start from scratch and type it all in. But this is a great helper. So we're going to read in our adjacency matrix, and it is the Karate Club adjacency matrix file. It's a CSV file, and we're gonna make sure that it reads that we do have headers, and we don't want to put the strings as factors. We want to keep them as strings, and we're gonna start our rows at 1. And so we're going to look at the head of the adjacency matrix. So we're just going to look at the first 5 rows, but it gives us all of the columns, but we can just look here. So here we have the first 5 actors: Mr. High, Raquel, Scott, Russell, Rocco, and Cheryl. And I believe this is the last few of the network, so we have a kind of like a good overview of who's in it. And just for an example of reading the adjacency matrix, Mr. High has a connection with Mirta. Raquel also has a connection with Mirta, and we can see that Scott has a connection with Liz and also one with Anthony. So this is just a good way to kind of get an overview of what you're looking to. So let's transform the data into a network format. So here we have, we've just looked at our network, or excuse me, as our data as an adjacency matrix. But now we want to use this network function in StatNet, I believe, to create a network. So we're putting in the data, we're giving the type of matrix an adjacency matrix. You can also put edge list if it were an edge list. So depending on the type of data you have, you can create the network from that. These nodes, actors, are not directed. And I think this is just to, I'm not exactly sure what this is, but it looks like it's needed. Okay, so we have our karate network and we're going to look at it. And this just gives you kind of like an overview describing the network attributes. So there are 34 vertices, so 34 nodes or actors in the karate club. It's not directed. There are no hypergraphs. There are no loops, so no one is connected to themselves. There's no multiple graphs. There's not a bipartite graph. So there's only actors. There aren't, for example, 2 types of karate clubs, just the one. So we're just looking at the actors. So total edges, so the total number of relations between the actors is 78. We aren't missing any edges. And yeah, so 78 edges is our edge number. And we're also looking at vertex attributes, and the attribute we have are names. So like I mentioned earlier, we have a list of names that work with the data. So let's just look at our network. Here it's just a simple visualization, but let's add some color to it to kind of be less boring. And I'll open this up. Cool. so here we have our network. Mr. High, who is at the top of the list, kind of branches off and has one section of the network. And Kim and John A have another section. And so we can just kind of see what's happening with this network and how it's kind of spread out. Let's see if we need to go back to. So, okay, yeah, so we want to save. Okay, so let's go back to the PowerPoint because that will be our next section of the workshop. Okay, so visualize networks, just an overview. The network on the left is what we just did and what we just went through. And the network, on the right, excuse me. The network on the left is another way that network analysis visualizes their data or their networks. So we have a partition matrix, which kind of just shows, it shows how actors are connected to other actors in kind of a more, not scatter plot exactly view, but it kind of shows better where things cluster and where there's more relations happening. An image matrix uses the same concept, but kind of simplifies it so that it's more blocked. My notes say one avoidance of network analysis is the ability to observe and analyze connections as a visual component. Some visuals are more useful for some things and some for others. So we would use the Karate Club network for a smaller data set and kind of these block matrices potentially for larger data sets. Okay, so while looking at the network, where there is some vocabulary and some concepts to take with you while you analyze your data. So components are minimal subsets of nodes that can reach one another. So it's a very basic type of subgroup in a network in which all nodes are connected directly or indirectly. Isolates are nodes with no links. So it's kind of this N guy right here. For today's purpose, we won't think of them as outliers, but as isolated nodes with no connections to anyone else in the network, although they're still part of the network. Density is the proportion of links that could exist that actually do exist. So essentially, if N were linked, where could it be linked to, and would it be linked to that? I guess more a clearer description would be the proportion of observed ties, which can be edges, arcs, or relations within a network, to the maximum number of possible ties. So of all the nodes in the network, what is the maximum number of ties that could be had? And compared to those maximum number of ties, how many ties does the node actually have? So when we're looking at density, when it's closer to 1, the network is more interconnected. And when we're looking at density, it does not look at ties between itself, so loops. Transitivity, is looking at kind of like usually a three group kind of connections. So if A is connected to B and B is connected to C, then A is also connected to C. It's usually looking at this kind of like if like my friends are friends. I'm friends with my friend's friends. So a friend of a friend of a friend is also my friend. I feel like this A to B, B to C, A to C is a little bit more clear. But it's kind of this like relation of like we're friends. I'm friends with my friend's friends. In kind of more advanced network analysis, it looks at how what if A and C are enemies actually, and how does that work for the network and what have you. And so just for the basis and for for our workshop, we're going to look at transitivity as friends of a friend of a friend. And reciprocity is when information sent from one node to another is reciprocated. And this is specifically for directed edges. Just as promised earlier, here are textbook definitions for all of these concepts. So you can look further into it later on in your research. More concepts. We're going to look at our karate network's centrality, and centrality tries to figure out a specific node's position within the network. And so there are three main types of centrality measures. There's degree centrality, betweenness centrality, and closeness centrality. Degree centrality looks at the number of links a node has. So regardless of direction, node X has 1, 2, 3, 4, 5 links. So their degree centrality is 5. When we take directed networks into account, we count the in degree and out degrees. So in degrees look at the information being taken in to the node. So X would also have an in degree of 5. And here in our out degree network, it would have an out degree of 5. And further looking at degree centrality, degree distribution is a probability distribution of these degrees over the whole network. So similar to some intro to stats or some stats, real world distributions are usually skewed, showing where kind of like here we have the network kind of splitting off into two clusters, I guess. Whereas random network distributions are more similar to a normal or maybe Gaussian curve. Another centrality that is kind of a subset of degree centrality and maybe not considered one of the main three would be eigenvector centrality. And this is the number of ties a node has weighted by the centrality of those ties. So essentially, some ties are more central than others. So if you're connected to those ties, you might also be central. So for example, a node with a high degree score, so maybe X is, excuse me, it could have, sorry, let me go back to this. So X might, regardless of the direction, it might have a high degree score, but a low eigenvector score because everyone that it's connected to doesn't have their own connections. So if we were to go maybe to C here, it would have actually a higher eigenvector than X in our previous visual, because the nodes that it's connected to have higher degrees. So these nodes, so for example, D has 4 degrees, and C has 5 degrees. And so we're looking at the number of degrees C has over the degrees of each of its relations. And so C would have a higher eigenvector than, let's say, F, because F is only connected to these 3 who might have lesser, well, I guess H is very connected. So I guess comparing C to X, although X might have the same degree as C, their eigenvectors vary greatly because all of these outside nodes aren't connected to anyone else. And so it kind of drops the eigenvector centrality, whereas C over here is connected to nodes that are also highly connected within the network. And so it's kind of like this idea, I guess, in social world of like, who do you know? Who do you know? Your friends who are very connected are probably more beneficial to helping you maybe get a job or do something that you want, more so than a friend who's maybe a hermit or something like this, or who doesn't have connections in a field that you're interested in. So that was kind of like a roundabout way of describing eigenvector centrality. And here is, I guess I could have come here. Here is kind of just like a example of all of these centralities and their descriptions, looking at all of these measures. And here again are the textbook definitions for these concepts. And I think we can go back to R now and look at some of these centralities. So, also, please let me know if I'm going too fast or too slow, or if you need me to change anything. But okay, so now we're at about line 54. And we're going to set up the network to look at its components, its isolates, and its members, and its density. And then we'll go into centrality measures. So we want to make sure that we save the names of the club members. So if you all remember before, our network attributes had our network vertex names. And so we want to make sure we set those names as our club members. We want to look at the components of the network. We only have one component, so we only have one network, right? There aren't any splits or I guess fissures within the network, for lack of a better term. And we want to see how many isolates we have, if there are any isolates. And we do not have any isolates. Everyone seems to be connected to another actor, if only by 2 or 3, or even 1 connection. So let's look at the density of the graph. How dense is our network? And it's about 0.14 density score. And so it's a little on the lower density side, because if you all remember, we're looking at density from a 0 to 1 scale, 1 being highly dense, 0 being less dense. And so I guess it's not too bad, but it is not as dense, and that's fine. This just helps us know how connected everyone is to each other. Okay, so let's look at our centrality measures. We'll start with degree centrality. So I guess I should, we're here, the degree function of StatNet is really, and much like much like isolates, it just write the degree, you write your network, and we're looking at our graph mode as graph. So that means it's just an undirected graph. If we wanted to look at a directed graph, we would just put digraph for short, directed graph. But we are not using a directed graph, so we're just going to stick with our graph network description. Okay, so let's look at the degree. We're going to add the names to our network so that we can understand who has which density. And now we're going to sort the degrees from lowest to highest. So let's, okay. All right, as you see here, John A has 17 ties, and Mr. H has 16 ties. So these are their degree measures, whereas Daniel only has one. And we can kind of see that if we compare, hopefully you can see it kind of okay. We can kind of compare the degree measures to the graph. So if we try to find Daniel, he's right here and he only has one connection to Mr. High. Whereas if we look at Mr. High, he has all of these other 16 other connections rather. Yeah, so let's go deeper into, excuse me, so just clarification, the higher the density, the higher the degree, the more people the actors are connected to. And we can look at a histogram distribution of our degree network. And here we're looking at it. We want to break it up by 12. This is just the title and the x-axis. And we're looking at our degree network. So if you look at that, here we have a high number of people with 12, excuse me, there are more people with lower degrees than there are people with higher degrees. So here we have Mr. Mr. High, excuse me, and John A, whereas here we have Daniel, Megan, Paula, Ina, Frida, etc. Cool, so let's look at our eigenvector centrality. And again, here is the function eigenvector centrality, our network, and we're looking at it as a regular, or excuse me, an undirected graph. We're adding names to the graph, and we're going to look at the eigenvector centrality. Again, John A and Mr. High are high up on our centrality measures, but if you look down here, Daniel is no longer the last. Tony is last, and the other actors, I believe they were Frida, Ina, I forgot who else, but they're all more in the middle, and so we can just see this because of I guess Frida and Ina's connections before, who they were connected to before, bumped their eigenvector degree up a little bit. So I guess we could also, yeah. And let's look at their closeness centrality. So how close is one person to another? Did we go over closeness centrality? I can't remember. So essentially, this is how densely connected someone is to another based on, well, let's oh, I guess I deleted it. Oh, I guess I didn't. I'm sorry. Excuse me all. Okay, so God, I thought I had a thing. Okay, closeness centrality is the sum of geodesic distance, so from a node to all other nodes. So geodesic distance is the shortest path possible from one node to another. So which node can most easily reach all of the nodes in a graph or a subgraph? And so here, B is our example. It can reach 3 nodes. And this is kind of like the great connector for these 3 guys to the rest of the network. And so B has is the closest node to all other nodes with the least amount of steps between. So this node up here has 1, 2 steps to get to B, and whereas it could kind of potentially take a bunch of other 1, 2, 3, and then 4 to B, and then continue going on. So B is kind of like the close, how close is it to everyone else based on how long it takes to get there. And betweenness centrality is the measure for how often a node is along the shortest path between 2 nodes. So essentially, which node has the most flow, control over the flow between 2 nodes in a group. So how much of a middle person can this node be? Because without C, none of these 3 kind of subgraphs around here would be connected, right? So this every node in each of these graphs needs to go through C to get to the rest of the network. And so C's betweenness is very high because it's kind of like the gateway to other parts of the network. Yeah, so sorry I didn't cover that. I thought I had a whole slide about it. So anyway, so now let's look at the closeness centrality. So here we're going to use our closeness function again, and we are going to, I think I already did this, with the same kind of thing, same kind of setup. But here we're looking at different degree centralities for different actors, right? Now Mr. High is closer to other people, so essentially he's closest to most people in the network. So to connect with Mr. High, it takes the least amount of steps to get there. Scott as well. Whereas before, John A used to have the highest degree and eigenvector centralities, and now he was kind of bumped to 3rd place. Again, if we look at the kind of lower end of our degree measure, centrality, closeness centrality measure, we are looking at Tony again as last compared to our eigenvector measure, and France is coming in. So essentially, it takes a lot of steps to get to Tony and France, whereas with Mr. High, most people usually have less trouble getting to those. And so let's see our betweenness centrality and look at how connected these actors are. And so here, again, we're looking at Mr. High has the highest betweenness centralities. So he's kind of the go-to person, or excuse me, go-to actor within the network to connect to other actors in the network. John A is similar in that sense. And if you all remember, let me just print out our network so that we can have a better view of what's happening. What? Come on. Well, maybe not. Okay, here we go. So let's go back to betweenness. Okay, so hopefully we can see. No, that's not a good look. Okay, here I guess it's fine. We have Mr. High, so he has a betweenus, the highest betweenus, which means people need to go through him to get to others within the network. And the same with John A. People need to go, and Kim, people need to go through them to get to other parts of the network. So these are kind of like how we can look at different centrality measures and what they might mean for our research and analysis. All right, let's go to the next section. Oh. Okay. So looking at our network, I guess if anyone wants to chime in, what is interesting about the network structure and why is it interesting?
Looks like there are two major groups between Mr. High and John A, and they're not very, they're connected, but not overlapping visually, at least.
Yeah. So yeah, what about individual actors might be interesting? Maybe those that might not be so densely connected. Essentially it's kind of like, well, they kind of keep to themselves in the club and kind of maybe just connect with a few people that they know. And so what we've learned, what might the centrality measures that we've gone over tell us about the karate club?
Maybe, I guess the first thing that jumps out to me is that you really need Mr. High or John A, or else the club might fall apart.
Yeah, definitely. And in fact, Mr. High is the trainer and John A is the club president. And I guess these are just to think of this outside of the karate club. What might be ways to further to use this in your own research or ideas? You don't have to share. You can put it in the chat if you like as well. But this is kind of like a good way to see how this could be used for your own work. And some nice questions to think about as well. Okay, let's see. So essentially, here's the story to give you background to the network, because a lot of times you get all of these measures and you analyze a lot of the data, and sometimes it doesn't give you the full story, right? You sometimes you do need a qualitative aspect to your work to kind of better understand what's happening. And so essentially, there was conflict between Mr. High and John A because Mr. High wanted to raise prices for classes, and John A didn't want that. He wanted to keep prices as they were, and so because this network was observed over, I think, a two or 3 year period, it was kind of looking at how the club became divided on the issue of raising prices for classes and not. Here, Zachary describes some of the supporters of Mr. High saw him as a fatherly figure who was their spiritual and physical mentor, and who was only trying to meet his own physical needs after seeing to theirs. whereas the supporters of John A. and the other officer saw Mr. High as a paid employee who was trying to coerce his way into higher salary. So these two people built fragments within the network that might have originally have been just like kind of one, maybe more densely connected graph. And so this is, I guess later on you can read this, but it's kind of just like the drama that happened throughout the relations and the meetings and confrontations within the karate club. And so it's kind of this like, we're raising prices. No, don't raise prices. And so it kind of split the group. So thinking of splitting groups or talking about splitting groups, when we look at splitting groups or subgroups at its basic form, we want to look at, they're called cliques. I've heard it being called cliques also. So I guess I'm in my head, cliques sounds is a little funny, but it has been called cliques. Anyway, side note, I'm going to use cliques because that's how I want to say it. Okay, so a clique is a subset of nodes where each node has a tie to every other node in the network. And they can be overlapping. Essentially, it would be impossible to add any more nodes to the clique without violating the condition where every node is connected to another node. So essentially, H, G, and I are a clique because they're each connected to each other. We could even say that J is part of this clique because it's connected to all of them, but J is also connected to K. Well, I guess I and H are as well. So these interconnections are less cliques and more communities, which are thought of as cohesive subgroups that can be shown by fragmenting the network. So here we can show this whole community, including K, as not exactly like splitting the network, but kind of becoming its own cluster. And here, L and M are also its own clique. So the way that cliques and communities have been found with large sets of data and kind of just for kind of more accuracy, there are algorithms that look at the network and say, okay, let's calculate the edge betweenness of the network, so the betweenness centrality, and find the edge or edges with the highest score. So once they find those edges with the highest score, they delete those edges, remove them. And then we look, are there still edges left between these kind of like communities? And if there are, then we go back and find the edges with the highest between the centrality and remove them again, and so on until we have these kind of concrete groups. So here there's one round of the algorithm and another round. So now we have, here we had 3 communities. Oops. Here we have, excuse me, here we have 2. Here we have 3, and another round of the algorithm. There's still 3 communities with 1 isolate. And so if we want to look at it in how the algorithm splits it up, we're looking at the three communities in its entirety without the cut fragments, and it'll find those and say, okay, great. We're not going to entirely remove the edges from the network, but the removal of the edges show us where different communities may lie. And we can see this with an example of a dendrogram. So here, this network with three communities is shown in our dendrogram or tree graph. So here are some more textbook definitions. And let's go to the code and check out how to do this. Okay, so essentially, here's where we're going to be using our iGraph package. It's the third package we're going to be using, but because, like I said earlier, some packages kind of conflict with other functions within a package. We're going to be using kind of this this setup where we have two colons of the package name and then the function name. So we're going to get our adjacency matrix again and rename it for this new set of analysis. So we're putting it again, our adjacency matrix into matrix form, just to kind of help support the iGraph setup and functions and their own needs. So now we're gonna get the iGraph object. So we have our package name and we have the function that we want to use. And so we're creating our network object from our adjacency matrix. And again, just like the mode, our G mode from before, we're using an undirected graph. So if we look at that, we created our adjacency matrix, and we're going to kind of simplify the object. So we're going to remove multiple loops. We're going to remove any multiple graph components that might have happened or gone through while converting, which probably didn't happen, but I think this is just good practice. So now after we have our simplified iGraph object, we're going to look at it. And it's definitely, usually takes a little more to kind of observe. But here we have our attributes, the names and our types of edges, which here we have our nodes and our edges. And our vertex names, and here it doesn't show you a full overview of what's going on, but it kind of gives you an understanding who Mr. High is connected to, and then Raquel and so on and so forth. But we can look more into it while we look at the vertex and the vertex or node and the edge set. So again, we have our package and our V meaning vertex. And so here, all of our vertices, so all 34. And then our edge set. So this is the first set of edges from our 78 edges. So now let's just plot it. Let's check it out. And so it's going to be similar to our previous graph, and just to give you an idea of what's going on, where we have our iGraph package. We want to plot the iGraph, and we want to plot our karate network. Our vertex size, so the nodes, is 10, and the label is 0.8. So the label would be our actor names. Hopefully, oh, okay. Not as visible as our other network, but this kind of gives you an idea of how iGraph sets up its networks. And it's kind of not the same setup as before, but, or I guess rotation, but it's the same network. So we have our network. We can see our network. Now let's find our clicks. Here we're looking for 3 clicks within the network. So we're going to get our iGraph package. We're going to get our clicks function, and we're going to use our karate network with a minimum of 3 clicks. And so let's look at the head, so the first 5 clicks of 3 that we have, or I guess for 6. And so here, our first click is Annie, Benjamin, and John A. And then we have Benjamin Kim and John A. And then Sarah Kim and John A. and so on. So essentially triads within the network. And we see that there are 58 triads within the network. So let's look at the number of clicks with a minimum of 4 nodes. So essentially we're looking at how many kind of closed networks are possible within the network. So now instead of using a click with 3 nodes, we're going to find a click with 4 nodes. And so we can see that these first 6 clicks, who is connected within each of them. And so here's Mr. High, Raquel, Scott, Russell, and etc. So let's see how many of these we actually have. We have 13. So now bigger clicks are becoming less apparent, which makes sense because our network wasn't as dense, was on the lower density side. So let's find maybe 5 clicks. How many 5-click nodes are there? And here we only have 2. Mr. High, Raquel, Scott, Russell, George, and Mr. High, Raquel, Scott, Russell, and Danielle. And so again, we have 2 clicks with length of size 5. And I would say we could potentially look here in the network, but maybe on your own screens, you can see it more clearly because for some reason my network plot is tiny. Okay. So let's now, any questions from anyone? I guess I should pause every now and then for some questions. Okay, thank you. Thank you, Renee. Okay, so let's look at communities. We have, again, we're going to use the algorithm we used before. It's the Girvan-Newman approach. So essentially, find the betweenness centrality and cut the ones with the highest betweenness centrality. So again, we have our iGraph package. We have our edge betweenness function, and we're looking at edge betweenness to create communities. And we're just going to throw in our karate I network. Okay, so now we're going to plot our communities in a dendrogram. So kind of like the plot that I had before. And here we see that there are 5 communities within this round. And here Megan became their own community. And let's see if we can, we can see the split. Here's John A's community. Here's Mr. High's community. And these actors along the edges and right in the middle, I guess, have created their own community based on their betweenness centralities. But let's plot it. Let's look at it in the fun network looking form. So again, our iGraph package. We're gonna plot the iGraph. We're gonna use our karate iNet network. we're going to so our vertex colors are going to be the communities and the membership. So from our communities, one of the attributes shows the membership to each community. And so here, Anna, Rocco, Tony, Dory, and Cheryl will be their own community, members of one community, and so on. And again, our vertex size is 10, and our label is, our text is 0.8. So here, hopefully, okay. So here we have our 5 communities. This one is the John A community. Here's our Mr. High community. Here's Megan, all alone with her own community because her degree centrality was high enough to be cut and create her own little solo faction. And then we have the kind of outlying communities here, and this definitely mirrors our dendrogram. What's interesting is Daniel is not their own community, kind of like Megan here, but I think it's because Daniel isn't really a betweenness, doesn't have a high betweenness, because you don't need to go through Daniel to get to anywhere else. With Megan, a lot of these nodes need to go through Megan, or I guess their options to go to the other part of the network are slim, and Megan is one of the main options to go from one point to the next. Okay, so we're going to look at, we gone over factions. We have not. So let's go back to our PowerPoint and look at the next form of how we can kind of split up this network. So here's a better view of our communities within the network. We have our 2 main communities, our smaller kind of fringe communities, and then our Megan community. And as you all can see here, Megan's betweenness centrality is high because a lot of these other actors do need to go through this centrality, this node to get to places. Okay. So we're gonna formulate hunches and kind of figure out how the community can faction off via ideological groupings. So here we have different communities based on their centrality measures. And now we want to kind of look at formulating hunches and kind of trying to understand maybe ideas or ideologies that might kind of split the network into its own groupings. So Zachary states the factions were merely ideological groupings, however, and were never organizationally crystallized. So there was an overt sentiment in the club that there was no political division, and the factions were not named or even recognized to exist by club members. So essentially, this rift between the club president and the trainer wasn't like officially noted or anything like that, but there was this sense of different ideologies and kind of competing ideas on how how classes should be charged, right? So to understand how this rift in ideologies might work, Zachary collected additional data on ideologies, which were recorded as binary information with a modifier. So based on the ideology of raising prices, Mr. High was strong. and John A was weak. And so it's kind of this like true, false, strong, weak binary value that we placed, that Zachary placed. So while we're looking at the network structure, does this make sense, and why? And what is your hunch about the relationship between ideologies and interactions, and why? You can put an idea in the chat. You can chime in if you like.
Yeah, this is Renee. So I'm not sure I understand the question being asked, but
Sure.
I think that Zachary is making the observation, but it almost seems that the observation is not accurate, or it's either like accurate or not accurate. Accurate in the sense that the people do not see that there are kind of groupings and divisions, ideological or political, really. And to me, it's like, well, clearly, and based on the kind of the other context you provided earlier, it seems that it is evident. So it's almost like this observation by Zachary is a contradiction to what we saw before.
Okay, yeah, I can see that. And I think because there wasn't a clear, you're right, there is no clear strong, weak, false, negative, false, positive, false or true, or whatever. There were more kind of smaller communities that might have cared, might not have cared. It is, I think what it is the researcher applying their own hunch to a thing and trying to see if that was true, and if it kind of worked for this analysis. Yeah, I mean, I agree in that sense. And also this study also, this was done in 77. And so back then I feel like I've gone back and forth because it does have some biases, because Zachary was part of the karate club as well. But he never really says what ideology he was he prescribed to. But essentially, I think because he was part of the club, and he knew that there were I guess these two conflicting sides that may or may not have been extremely important to everyone, but they definitely were able to be shown when asked. So kind of do you agree with raising prices, yes or no? So I guess if you're looking at this and you want to learn something about it, you kind of get more information on that ideology or the attribute to the node. So Mr. High was strongly for raising prices, whereas John A was definitely not. And so this is kind of an easier way to break up this factions of the network and kind of see where people might fall closer to one another. But it's definitely kind of a overreaching view of how it might happen. And just much like a lot of other analysis, or I guess network analysis, especially social network analysis, has this kind of thing where privacy is hard to look at, but also ideologies and perceptions of relationships are very hard to pin down, because one person might think one thing about another and it might not be correct. And so I think this, much like in a lot of other applications, binary, looking at it in a binary way is kind of an easy way to figure out who's on what, if you're on one side or not. And I think for the purposes of his analysis, this kind of helped look at this question of who is more on board with raising prices, from my understanding.
Oh, that's helpful to me. Thank you.
Good. Yeah. Awesome. Cool. Let's go to the next. I'm sorry, any other questions or comments? So looking at different nodes, we're looking at characteristics of nodes. So for example, in our example, ideologies, and these are called node attributes. And so a smaller example, these nodes of our very basic graph from before, Lisa, her attributes are female and likes hiking. David is male and likes hiking. Emma is female, likes hiking. Mark is male and likes bowling. And so these are attributes, fairly simple. And then homophily is an idea that people who are more likely to connect with others who are similar to them. So here, Lisa, David, and Emma are connected because they all like hiking. And so this is a homophily of different attributes. So essentially the theory is if you have similar attributes to someone else or another community, you're more likely to be connected to them, and those communities are more likely to be their own kind of clusters or communities. And so that's kind of the idea, excuse me, of the Zachary ideology. So there are attributes of for or against raising prices can create a homophily of people agreeing with each other and connecting in that sense. And so in that sense, there's an idea of social influence, right? So people learn or adopt from others with whom they're connected and might potentially connect even more or further with that community as they become more involved, or they can not like what's happening within that community and kind of step away. And so this is kind of this can kind of snowball into segregating different parts of a network very, very easily and very fast. And I guess a whole other aspect of network science would be, especially not social network science, would be to look at like the strength of ties and how strong ties, so higher weighted ties, specifically within cliques, can just kind of keep to themselves and keep information to themselves and never grow or never kind of evolve or sometimes even survive, whereas weaker ties might help broaden perspectives and kind of connect these kind of segregated homophilies to the rest of the network or to the rest of the environment or ecology to kind of survive and use outside resources in a kind of linkage way, like not a associate, what is it? Like a friend that's not a close friend. Oh my God, I'm losing the word for acquaintance. Gosh, sorry. So essentially, Lisa, David, and Emma have really strong ties, whereas Mark is a weak tie coming into this kind of homophily group. So that's like a side section of social network analysis where weak ties actually might help in connecting segmented, like strong, kind of closed off groups to the outside world. Little tangent there, but let's look at the attributes of our network nodes and see how they split up the network. Okay, so we're going to read in our Karate Club attributes. So this is the data set that Zachary went and collected after the network was, or just to get more information. So we're reading in our CSV attribute file. leaving our header, making sure it knows we have it there, and we're keeping our strings as strings. Okay, so let's look at our faction attributes. And here it looks like we only have, so we have 2 factions. Let me look at the tail. So we could be a better. So we have, if we look at faction 1, Mr. High is in faction 1, John A is in faction 2. And this is the club after the faction, and I think that's just helpful to the faction data to split in that way. We're going to add these attributes to our karate network. So we're going to pipe in our vertices. So V here is stands for vertices. So we're using faction. We're adding faction to our attribute vertice, and it is, I guess, the column aspect. So we're looking at that guy. We can actually see if we can. I can't remember if this shows us cool stuff. No, let's see. Oh yeah, here we go. So now instead of, so now we have, instead of just the vertex names, we have the vertex names within each faction. And the rest of the network setup is the same. Cool, and so let's visualize this new network with 2 different factions with 2 different colors. So we're looking at faction 1 is Dodger Blue and faction 2 is Hot Pink. But we want to keep the labels and we're making the node colors the faction. Okay, let's open this up. Okay, so here we can kind of see how there is a split between John A and Mr. H. It's kind of a more general split, not based on measures of centrality. It's based on ideological attributes. So here we have 2 types of ideological attributes, which is understandable because or rather Zachary collected data in a binary form. So it's going to be one or the other. Sorry, my slide is popping up. So here we have our 2 factions. I'm guessing Mr. H was strong for, in the example, I'm not sure if this was exactly what happened, but Mr. H was strong for raising prices, and Kim and John A were weak for raising prices. Oh, wow. Okay, so that is all we have here. We're looking at factions. Let's go back. Here's probably a better way to zoom in and check it out. So, okay. Here we have our 2 attribute factions that connect to groups on either side. Now Mr. High is on the left instead of like in the R plot. And here initially is the faction, and then I guess club membership after meant after kind of after the 2 years had passed and how ideology might have changed, and it only changed for one actor. I guess, excuse me, sorry, to give a background. I'm thinking that Zachary collected data in the beginning of the study on ideologies, and also towards the end after after the event might have been might have happened or something resolved rather. And so this looks at the before or the original faction and the after faction. So looking at club membership ideologies after the fission of the price raising, only one member switched to Mr. High. And so it's what is really beneficial about network analysis is that you can actually just kind of look at two different networks and see how they differ before and after an event, which is kind of beneficial if there are kind of more apparent changes or drastic to show that that how drastic something might have been. It's sometimes the visual is very appealing to show impact. Oh, I guess I don't have this, but we can just check it out. I will put this over here and we can look at it based on how am I on time? Okay, I have about half an hour. So let's type in this code over here. So I'm guessing in an earlier workshop, someone asked to check out the coordinates. Use coordinates in plot. So let's check it out, just to explore. So we're gonna write in coordinates, see what they were doing. Gplot. Oh gosh. Layout. Oh, it's a different it's a different layout. Coordinate. Okay, so let's look at the X and Y coordinates and see what this is. I guess I should have done this before. Sorry, y'all. I will. I spelled it wrong. Okay. Wow. Okay, maybe not. Maybe we can just continue. I know I'm misspelling things, so I apologize. Oops. Well, okay. Well, this code is in the PowerPoint, so we can just go about it. You can check it out later and see what happened. Okay. So here's kind of another overview of what happened with the network and the club, and how the event of raising class prices was resolved. Specifically looking at Emily, person number 9 here, Emily was a weak supporter of John, but joined Mr. High's club after the split. This can be explained by noting that he was only 3 weeks away from a test for the black belt master status when the split in the club occurred. So let's look at essentially it's just the split was the political crisis of raising the price or not. Okay, so here, just a recap of what has gone on during this workshop. We looked at nodes, edges, and node attributes. We looked at graph characteristics, data formats, network structure, actor position, subgroups, homophily, and social influence. And we, in R, we visualized a network. We explored the overall network structure, actor positions. We looked at cliques and communities, formulated and explored some hunches based on ideological attributes. And we, this data set is one of the most prominent kind of intro to network analysis in the network literature, because it's a great example of how to show a lot of these concepts. And so if, I guess if anyone has any questions, I'm more than happy to answer them. Yeah, I actually, for some weird reason, just saw Karate Kid this past weekend. So that was a fun blast from the past. I haven't seen Cobra Kai, but it's a spinoff, I believe, from Karate Kid.
It's the Karate Kid in the present day, and there's competing factions. So you might see a lot of your network analysis and the different groups of people and how they are competing and interacting and have relationships between the groups.
Yeah, that's very cool. I thought it was like the bad guy from Karate, or the mean high school dude from the Karate Kid movie now has his own dojo or something, correct?
Yeah.
Okay,
exactly.
Cool.
But
awesome.
you get more into the personalities. But anyway, the relationships become complicated, and your analysis is making me think of that. How they're not straightforward at all. But they're karate anyway.
No, thanks. That's a great connection, and that's kind of just like how the world works, right? Just like nothing is really set in stone. Kind of like how Renee suggested, like. What do you mean? It can't just be one or the other. So yeah, definitely. Cool. Well, I know we're a little early, but I think unless, here's our sources, but I think unless we don't have any other questions, I think we can end. What do you think, Austin?
Yeah, if there's no other questions, we can go and end. I'll go ahead and stop the recording just in case.
Sure.